Have you ever wondered how your social media feed just updates instantly all over the world? Or how an online store knows the exact stock of an item in real time? Well, a huge part of that magic comes down to one of the biggest puzzles in software architecture: how you manage distributed objects. Today, we're going to break down how systems handle data when it's literally scattered all over the place.
So, what exactly is a distributed object? You could think of it as a single thing, right? Like your user profile. But its information, its state, and its behavior are actually spread out across multiple computers in a network. The real trick, the absolute goal, is to make it feel completely seamless and local to you, no matter where in the world the data actually lives. Here's a simple way to think about it. Imagine a chef, that's the logic, the behavior of an object, is in, say, New York, but all their ingredients, that's the data, are in Los Angeles. How do they possibly cook the meal? This is the fundamental problem we're talking about. We've separated the action from the actual substance.
Okay, so here's our game plan. We'll start with the main challenge. Then we'll look at the big architectural blueprints that engineers came up with to solve it. After that, we'll get into the nitty-gritty of how you actually find and move these objects around. Then we'll tackle the massive problem of keeping everything in sync, and finally wrap it all up with why these choices matter so much.
This brings us right to the heart of it all, the biggest architectural problem that every single distributed object system has to solve. Where should the work actually get done?
Yeah, it all boils down to this one question. When the chef and the ingredients are in different cities, where does the cooking happen? Do you fly the chef to the ingredients, or do you ship all the ingredients to the chef? Believe it or not, this is the fundamental choice that shapes everything else.
And that one decision creates 4 possible scenarios. The first one's a no-brainer. The code and the data are already in the same place. Easy. But for the other 3, you have to make a call. Do you bring the remote data over to the local code, or do you send the code over to where the data is? Each path requires a totally different architecture and has massive implications for performance.
So how do we actually solve this puzzle? Well, engineers have come up with 2 main blueprints, and they're both based on that classic client/server model. Let's take a look at how they each try to tackle this distribution challenge. This leads us to 2 very different philosophies. First, you've got the object-server model, which uses what's called function shipping. Basically, the client asks for a specific, logical thing, and the server does all the heavy lifting to figure it out and send it back. Then you have the page server, which uses data shipping. It just sends over big, raw chunks of data, and the client has to do the hard work of sifting through it all.
Let's dig into that object-server model a bit more. In this world, the server is the brain of the operation. It's handling all the complex stuff, optimizing queries, managing transactions, you name it. The client's job is way simpler. It just gets the finished, polished objects. This setup creates what we call a heavy server and a light client.
Now let's flip it around and look at the page server model. Here, the server's role is much simpler. It's basically a glorified file server, just grabbing physical pages of data off the disk and shipping them out. All the complexity, figuring out what data belongs to which object, processing it, all of that gets pushed onto the client. This means you have a simpler server for sure, but you end up creating a heavy client that needs a lot more power and smarts.
Okay, so let's say we've picked our architecture, but how do we actually handle the logistics? Let's talk about the practical challenges of just finding these objects and moving them around the network.
All right, here's a key technical term you gotta know. Pointer swizzling. You see, on a disk, objects refer to each other using these identifiers, which are kind of slow to look up. But when you load that data into the client's super-fast memory, you don't want to be doing those slow lookups. Pointer swizzling is the magic trick that converts those clunky identifiers into direct, lightning-fast memory pointers. It is absolutely critical for performance.
So how does an object actually pack its bags and move from one machine to another? Well, first, the system makes sure it's in a ready state. Then it ships the object over to its new destination. But here's the clever part. To keep track of it, a proxy object is left behind at the original spot. It acts just like a forwarding address, always pointing to the object's new home.
Now, this brings us to what is honestly one of the trickiest problems in any distributed system, especially in those data shipping models. It's called cache consistency. How on earth do you make sure everyone is looking at the same up-to-date information?
You don't have to take my word for it. The source material puts it perfectly. It says that because data is shared by so many clients, managing all those copies for consistency becomes a serious concern. And that's putting it mildly. This isn't some side issue, it's a central design headache.
Let me put it this way. Imagine you and I are both looking at the last ticket available for a concert online. If you buy it, how does the system make sure my screen updates immediately to say sold out? If you don't get that right, you just get chaos with people working off of stale, totally wrong data.
So after looking at all these challenges, it becomes pretty clear that there's no single perfect solution. There's no magic bullet. Choosing an architecture isn't about finding the best one. It's all about understanding and navigating a series of really critical engineering trade-offs.
This table really lays out those core trade-offs. You see, object servers give you those light clients but put a heavy load on the server. Page servers do the exact opposite. And network traffic? It's a toss-up. An object server is great if you need one specific thing, but a page server might actually be better if a client needs a whole bunch of related data at once. And then there's data clustering, basically how data is physically arranged on a disk. Page servers really care about this because they're grabbing whole pages at a time, while object servers, not so much.
So here's the bottom line. It's all a balancing act. You are constantly trading off the workload on your servers against the complexity you're willing to build into your clients, all while trying to keep your network from catching on fire. It's a huge strategic decision, and there is no single right answer.
And that leaves us with a final thought to chew on. As our world gets more and more interconnected and our systems get even more distributed, what do we start to value more? Is it the raw, screaming performance you can squeeze out of a super complex, highly tuned system? Or is it the simplicity and the maintainability of a system that might be a little less optimized but is way easier to manage? The answer to that question is what's going to shape the next generation of these incredible systems.